Hi to everyone and welcome to this Teledyne E2V webinar. Right now I'd like to introduce today's presenter, Mark Holdaway. Mark has over 30 years of experience in defining and taking new semiconductor products to market in the high-performance analog world. He previously worked with National Semiconductor, Exynol Technologies, and Intersil. Now, since 2013, Mark has divided his time between consulting for leading semiconductor manufacturers and working to build his own technical content-focused company. He maintains broad interests across the semiconductor space and has the ability to dig into engineering detail, yet be able to remain detached and see the strategic implications of technologies. So Mark, welcome to today's event. And with that, I'm going to pass things along to you to get us started. So Mark, go right ahead.
A warm welcome and thank you for joining this webinar on Get Going with ESIstream. This is the second part of a series on ESIstream and is focused specifically on getting to grips with applying the new ESIstream IP packages, which have been finalized this year by Teledyne E2V. Hello there, I'm your host Mark Holdaway, and over the course of the next 40 minutes or so, I hope to provide enough background information to enable you to unpack the IP packages and start a new project. I've tried to include here a number of the commonly asked questions we receive from our customers as well. ESIstream is an open source, high-speed serialized data link technology which provides an interconnect solution on a par with the industry standard JEDEC JESD 204. In fact, as we will show, ESIstream offers some enhancements to the industry standard. In a sentence, ESIstream's like JESD 204, but easier to deploy and work with. Before we get down to the nuts and bolts of ESIstream, let's quickly review the content of this seminar. Firstly, it makes sense to recap the basics of ESIstream. Then I'll introduce the IP packages and provide an overview on topics including how you choose the right package for your specific application. Then we look at starting a project and what's involved. I want to focus some time on an ESIstream enabled broadband data converter from Teledyne E2V's portfolio. This is the EV12AQ600 family, featuring 8 ESIstream data lanes. We'll consider the clocking requirements for different data configurations. Along the way, you'll learn about some of the unique clock capabilities built into the ADC, including the sync chaining feature. I'll round up this review by highlighting some of the latest development projects that will expand our ESIstream portfolio further, and then we'll cover a few of the frequently asked questions. Let's recap on ESIstream and answer the questions: what is it and what can it do for you? ESIstream, like JEDEC JESD 204, is a high-speed serial data interface used primarily to connect data converters to field programmable gate arrays or FPGAs. ESIstream is a highly efficient serial link technology based on current mode logic transceivers. It's based on a 14-bit 16-bit encoding scheme and targets primarily 12 and 14-bit resolution high sample rate data converters. It's available as an open source alternative to the JEDEC system, but though there are similarities between the two, ESIstream has some system level advantages, as we'll soon see. So what about those advantages? Firstly, there's flexibility. This is an open source, license-free protocol. We provide full documentation, and users are welcome to modify the design files to include any technical enhancements that they specifically require. ESIstream uses an efficient coding scheme, achieving 87.5% efficiency, meaning more data throughput and less overheads. ESIstream remains relatively uncomplicated in digital design terms, meaning that it typically requires less hardware resources in terms of lookup tables than equivalent JEDEC implementations. That translates into reduced power consumption and greater economy. In some systems, especially communication or radar applications, latency is critical. Latency is the time it takes for sample data to emerge from the data conversion block, and in those communication systems, time often represents absolute signal phase, so it needs to be deterministic and minimized. And finally, as already mentioned, ESIstream is an economic solution. What are the high-level features of ESIstream and what can it do for you? Important in many signal processing applications, such as beam-steered systems, like used with highly agile radar, as well as in comms and electronic countermeasures, is deterministic latency. Deterministic latency ensures that a target system remains on top of the all-important signal phase information within the design. Synchronization is ensured through a unique to ESIstream sync signal. Unlike with JESD204, ESIstream does not rely on the expense of an additional precision clock. Rather, as we'll see shortly, it uses a relatively slow pulse that can be chained through multiple devices and is retimed at each active component in the chain to enable a mass of converters to operate as if being one ultra-high channel count single device. ESIstream is currently supporting designs up to 12.8 gigabits per second and has been demonstrated to work in a variety of settings, both single board designs and across backplanes. ESIstream, in common with many serial links, ensures DC balance by limiting the maximum allowed running disparity to plus or minus 16. The link protocol includes the ability to monitor system synchronization through the provision of a clock bit. The protocol includes encoding that ensures a minimum number of level transitions to enable clock data recovery, whereby the maximum run length is kept. I'm hoping there was nothing new to you in the last few slides and that you feel comfortable digging into the specifics of the new IP packages now. The next topic to consider is what's available and how do you go about choosing the right variant for your needs. The first piece of news I'd like to share is that Teledyne E2V has recently released its latest version of the ESIstream design resource website, which can be found at www.esistream.com. It has a slightly different look and feel today and now includes several new repositories of information. Notice here the highlighted IP package link. This is where you will find all the information for the various packages I'm going to discuss now. The latest packages extends tested data rates up to 12.8 gigabits per second, as validated with the EV12AQ600 ADC. The new packages support multiple frame widths, allowing users to trade off latency with FPGA clock rates. We provide support for several widely applied FPGAs. Customers can now select IP packages with either 16, 32 or 64-bit data frame widths. For the older Xilinx Vertex 7 FPGAs, there's a 16-bit data frame package which can be evaluated on Xilinx's own VC709 board. In addition, for 32 and 64-bit framing, there's an IP package targeting the Xilinx Kintex UltraScale KU040 FPGA deployed on the KCU105 board. Finally, for Intel Aria 10GX FPGAs, we provide a 64-bit wide data frame IP package. With this slide, I want to give you a sense of the user interface within the ESIstream website. When clicking on the IP package link at the top of the ESIstream site, this will take you directly to this following page where you can see 3 individual links to IP packages highlighted. This leads to the most obvious question: which of these 3 links is the one you need for your project? Well, in the case of Intel, it's pretty straightforward. However, in respect to Xilinx, it helps to understand what data frame length you need, and this is what I intend to explain next. We'll talk shortly about what differences the frame length makes with respect to determining the correct IP package to use. In this table, we show the relationship between the various supported FPGAs, their evaluation boards, and the frame length. Once you understand the importance of frame length selection, you'll know exactly which IP package to target. In the case of the latest Xilinx Kintex UltraScale FPGAs, we have support for frame widths of 32 and 64 bits, working up to a full data rate of 12.8 gigabits per second. Here, the primary target FPGA is the KU040 Kintex Ultrascale. However, this IP package can also be deployed with the KU060. For these two IP packages, the supporting hardware includes the KCU105 evaluation board from Xilinx, coupled with Teledyne E2V's ADC board, the EV12AQ600 FMC. This combination of hardware is illustrated in the image on the left-hand side here. For the older Xilinx Vertex 7 FPGAs, we also have IP support for 16-bit data frame widths, running with lane rates up to 6 gigabits per second. In this case, as illustrated in the image, the hardware includes Xilinx's own VC709 evaluation card, combined with the EV12AQ600 FMC board from Teledyne E2V. All of the Xilinx development boards mentioned are available directly from the manufacturer or via usual commercial outlets. For Intel FPGAs, we offer a 64-bit IP package supporting a lane rate up to 10.3 gigabits per second. This supports the ARIA 10GX FPGA. Support hardware once again includes the EV12AQ600 FMC board from Teledyne E2V, working in combination with the Attila ARIA 10GX evaluation kit, this time available from Reflex CES. To track down the Reflex CES system, simply search the web for Reflex CES ARIA 10GX FMC board or DevKit. Several times already we've mentioned the topic of data frame length, and as we've previously stated, Teledyne E2V is now offering IP packages at 3 data frame widths, 16, 32 or 64 bits. But in reality, what does that really mean? The best way to understand this is to introduce you to an ESIstream enabled data converter, and here's just such a part. This is the EV12AQ600. It features 4 independent 1.6 gigasamples per second ADCs connected to a 4-channel crosspoint switch. Each core can sample independently, however the crosspoint switch enables cores to be interleaved either as 2 pairs or as all 4 cores together, enabling the converter to sample with a maximum 6.4 gigasamples per second. With such versatility, data framing at the transmit end of the chain can be quite confusing. So let's take a closer look at that. This block diagram shows a signal connected to a standalone ADC. The ADC in turn is connected via multiple serial data links to an FPGA. The serial data is received by the transceiver, and each individual lane is processed by the ESIstream receive IP as shown. The received data that emerges from the transceiver may have been encoded by the transmitter into either 1632 or 64-bit frames. Irrespective of that framing choice, the data width expected at the output of the decoder is just 16 bits wide. Recall in the initial recap of the ESIstream protocol, I mentioned that it deployed at its core 14-bit, 16-bit encoding. 14 bits of data is combined with 2 ancillary bits used by the protocol to ensure sync locking of the interface and to maintain DC balance across the link. In referring to data frame width, this then is a design choice. It's one made at the transmit end of the link. As we'll soon see, that choice centers around the latency of data traveling through the system and the speed of the digital logic required to deal with the data processing. Each ADC core has a pair of serial data lanes associated with them. To understand the data structure and specifically the data frame width choice as data moves through the various components of the serial link, let's focus on the compound single channel of data formed when all 4 cores have been interleaved within the ADC. In this case, as shown here, all of the data is supplied over the C lane pairs as designated CSL0 and CSL1. The data seen at the output from the transceiver, therefore, will either be 2x32-bit or 2x64-bit frame widths. As the received data moves through the ESIstream lane decode system, the resultant decoded data formatted into 16-bit words means in the case of 32-bit data frames, 2 times 16-bit words will be available at the decode output. Whereas if a 64-bit data frame is used, then 2 times 4 16-bit data words are available. In these timing diagrams, you can see how an 800 MHz data clock at the transmit end of the link within the ADC is received by the transceiver within the FPGA as 4 data words at 400 MHz per lane. With 32-bit data framing, that's the characteristic shown in the lower middle of this slide. Or in the case of 64-bit framing, 8 data words per lane, seen here on the right-hand side of the image. This basically summarizes how data frame width impacts the data processing system. Over the last few slides, we've seen how data frame width affects system design choices. Selecting the narrowest data frame means achieving the lowest system data latency, and for many applications, latency is the major design criteria. At the far end of the link, the 16-bit wide frame leads to the highest frame clock frequency, which in some cases may stress the receiver and design margins. Moving upwards through 32 and then 64-bit wide data framing increases system latency. However, the wider the data frame, the lower the frame clock frequency, allowing the use of slower FPGAs. There is a direct relationship between the ADC sampling frequency and frame clock rate, so it's important to understand that changing the ADC sampling frequency also changes the transceiver lane rate. You should therefore check that your FPGA transceiver can accept the lane rate imposed by the sampling frequency of the ADC. For example, consider that the space-level FPGA RT4G transceiver from Microsemi has a maximum lane rate of just 3 1/8 gigabits per second, which is about a quarter of that needed to support the highest data rate mode of the EV12 AQ600. The ADC sample clock determines the bit rate on the serial lanes. The bit rate is twice the clock. So for example, with a sample clock of 6.4 GHz, the bit rate is double that at 12.8 GHz. At the transceiver end, a frame clock reference tracks received data frame boundaries. Hopefully, it's obvious that the frame clock rate is the bit rate divided by the data width of a frame. So assuming you selected a 32-bit wide data frame, then your frame clock frequency is equal to 12.8 gigasamples per second divided by 32, which equals 400 MHz. Given this, it's also clear that using a longer 64-bit frame, we halve the frame clock frequency, providing a 200 MHz rate. This table shows the various system clock relationships. On the left-hand side, you see the sample rate, the associated line rates, and then it provides the respective frame clock frequencies for 16, 32, and 64-bit framing. The framing choice has practical implications, which are highlighted especially for the 16-bit case. For example, clock rates higher than 4.5 GHz, the frame clock exceeds 500 MHz, which in turn exceeds the practical processing limits of what's possible with the current crop of FPGAs. This then becomes a fundamental limit of system performance, forcing developers who want to be able to use and sample at greater than 4.5 gig, that they have to select a minimum 32-bit wide frame in this case. I should highlight it's perfectly possible to develop ESIstream IP to support even wider data frames such as 80 bits, further lowering the frame frequency. However, that is predicated on the ability of the FPGA transceiver to support the frame rate. I just want to take a quick look at the various system level latencies that a designer will have to consider. In this example, the latencies identified have 4 separate sources. There's the latency through the ADC, it's fixed, and that's around 22 nanoseconds here. There will be a finite latency as the data travels through the serial link to the FPGA. The latency through the transceiver, as shown in this table, is influenced slightly by the data frame width choice, but contributes a further 20 nanoseconds to the total budget, roughly. But by far and away the largest contributor to latency in this system is that through the ESIstream decoder. Seeing these results clearly highlights how important the choice of frame data width really is. So in conclusion, when choosing the right IP option, the issue is a trade-off between the frame clock frequency and the receiver link latency. The 64-bit IP package becomes ideal when the receive link latency is non-critical in your design. It reduces the timing constraints and complexity within the FPGA. A 32-bit IP package choice offers the lower receive link latency, but again increases the FPGA frame clock frequency. You now have the means to select the correct IP package for your project. If you decided upon either the Xilinx 32 or 64-bit options, then when you click on Download from the ESIstream website, this is the next screen you'll see. You can clearly identify two separate zipped file containers, as shown here. So let's get started with the project. When opening the zipped IP package, you'll face 6 directories as seen here. The first, labelled KUS, contains Vivado-specific FPGA IP files, specifically for the transceiver receive and transmit blocks. These have .xci file extensions. The next 3 directories contain the VHDL source code for the IP, separated into common functions, receive and transmit, as is clearly visible here. The final 2 subdirectories contain 2 separate projects. These projects differ in terms of the hardware they're designed to operate with. The first project handles data streamed from the previously mentioned EV12AQ600 ADC board. The second project is a bidirectional loopback design using XM107 boards. To start a project, the first step is to open Vivado 2019. In the menu bar, scroll over to the Tools drop-down option, select Run TCL Script, and then locate the TCL script in the Vivado TXRX directory. In the second stage, Vivado will generate the project and an FPGA program bitstream file will be available. The final stage is to load the bitstream to the target FPGA using the hardware manager file. From here, the TCL file can be modified and resimulated just like any other Vivado project. Once satisfied with the current project, the IP code generated can then be downloaded to the target FPGA using the hardware manager. The second project is interesting as it provides simulation of both the transmit and receive IP elements, helping you gain real insight into the operation of the ESIstream protocol. This is fully explained in the accompanying technical documentation. Find and load the specific test bench you want to simulate as shown here, then launch the simulation. The Vivado environment offers a waveform inspection via the Virtual Logic Analyzer window, seen here in the lower portion of this slide. The switching behaviour of individual data lines are clearly visible. Note here the transceiver data TX line, i.e. the fourth waveform from the top, highlighted. With the sync signal asserted, there's a period of time for full lock to be established on the transceiver data TX line. However, once locked, the frame alignment sequence or FAS starts. That's clearly visible here by the unique comma or framing code FF0000FF being sent on the transmit line. I encourage you to interact with this project if you're keen to more deeply understand the ESIstream protocol in action. I'd now like to take the opportunity to talk a little bit more in detail about a device that implements ESIstream, namely the EV12AQ600. In doing so, we'll look at some of the clocking issues and how to manage data framing within the FPGA. This block diagram provides a high-level view of the data converter. It's a high-end wideband device. Signal inputs are applied on the left-hand side and flow into a broadband cross-point switch, featuring a full power bandwidth of 6.5 GHz typically. This switch gives the product considerable flexibility. For instance, it allows the individual inputs to be interleaved, enabling single, dual or quad channel operation. In the center of the IC, you'll see the 4 independent ADC cores, each of which is then connected into the ESIstream encoding block. The device features an ultra-low jitter clock management unit. This device provides data output over 8 serial data lanes. Each support a data rate up to 12.8 gigabits per second. This block diagram focuses in on one of the many advanced timing features of the ADC. That is the slow output clock, designated SSO here. It's a clock that runs independently to the system synchronization signal. SSO is an LVDS or low voltage differential signaling signal generated within the ADC that takes the sample clock frequency and applies a division by 32 to it. When applying this signal in a multi-device environment, only one ADC's SSO clock can be used as a deterministic reference clock. In the following few slides, I'll show you how to use this SSO clock to simplify generating the frame clock reference signal for the FPGA that we've previously discussed. This first example is a 64-bit frame width application. In this case, the SSO clock can be used directly for the frame clock reference. For this reason, it's directly connected to the transceiver's ref clock input. This next example is for a 32-bit data frame. As we've already seen, in the 32-bit case, the frame clock runs at twice the speed of a 64-bit data frame. To handle that difference, a 2x multiplier is inserted between the ref clock on the frame clock inputs within the FPGA. In this final example, again implementing a 32-bit data frame, we're using an external clock generator to provide both the ADC's sample clock and the FPGA's frame clock. Similarly to previously, the frame clock needs to be double the rate of the SSO. That is achieved here within the clock generator by a divide by 64 circuit directly after the voltage controlled oscillator seen here. I want to continue the theme of system clocking and consider specifically how to establish synchronization across a large data acquisition system now. So far we've taken it as read that time synchronization is important, but the question is why? Well, there are many systems in use today that rely for their basic operation on maintaining the integrity of precise signal phase information. In this example, we see an array of 5 separate antennas, each separated from the other by a distance d, labelled here in green. There's an incoming signal source to the northeast of this antenna array at an angle theta from the horizontal. The variable tau quantifies the delay in receiving the incoming signal at each antenna in this array. Tau varies as a function of the angle theta of its arrival at the antenna. Any time delays, especially variable ones across the electronics that samples the received waveform, will create phase error in the system. The physics of this system, highlighted in the diagram, is that applied in many beamforming radio and RF systems in widespread use today. So to minimize phase errors in signal sampling, it's critical that every individual channel is phase locked to a known reference. This is synchronization in action. In practice, multi-device synchronization for many systems is a major challenge. It complicates clock design and distribution. In particular, it may make designing printed circuit boards painful, especially as differential trace links need to be matched. There are several methods by which engineers aim to ensure sync. In the design of the EV12AQ600, Teledyne E2V gave careful thought to this problem, resulting in a unique sync timing concept. The ADC provides a pair of sync signal pins, the sync trig and sync output pins. These pins can be cascaded across multiple devices ad nauseum. A relatively slow rising pulse of around 5 nanoseconds is supplied from the FPGA to the first ADC's sync trig input. The first sync output is then cascaded onto the next ADC in the chain. This is known as sync chaining. And what makes this feature powerful is the fact that as the sync signal passes through each ADC in the chain, it is retimed to the original sync signal from the FPGA. Synchronization is thus ensured by putting the system through a single cycle training process. Once synchronization is rock solid across the system, it will not change, even under circumstances where the environmental conditions change, such as temperature rises. Teledyne E2V has a white paper discussing this topic in detail. Furthermore, there's also a short video explaining the benefits and performance of sync chaining available on the website. Here's two sampled signals in perfect phase alignment. In this diagram, the green and the black waveforms represent two separate sampled channels. The sync chain helps ensure that both sampled channels are time aligned, irrespective of whether they are neighbouring channels within a single data converter or local channels across an array of data converters. This is sync chaining in action. So I'm nearing the end of this nuts and bolts review of applying ESIstream, and I'd like to take a moment to consider some of the ongoing development activity here at Teledyne E2V. In the data converters domain, I've talked quite a bit about the EV12AQ600 today. This is a quad 12-bit broadband converter. The part is now fully released. It features a spurious-free dynamic range better than 70 dBFS, all the way up to 6 GHz. It offers C and S band operating modes and can perform direct RF down conversion in the C band. It gains considerable versatility from the embedded wideband crosspoint switch that facilitates interleaving of the ADC cores. And as we've seen, system synchronization is guaranteed through the novel sync chaining feature. In the very near future, we'll be introducing a dual 12-bit broadband multi-Nyquist digital to analog converter, featuring a sample rate beyond 6 gigasamples. It also will have extended dynamic range and programmable output modes. Incidentally, we haven't finished developing the ESIstream IP capability. Recognizing the importance of decode latency, as we've discussed today, we are currently readying a new 32-bit data frame package to support Xilinx KU040s. This will more than half the latency of the current package. In fact, decode latency should be around 12.5 nanoseconds. Its low latency package will be available in the new year. If you're interested in this, feel free to register that interest by contacting us at the web link shown here. A few final words on some other topics relating to ESIstream. Let's return once more to the ESIstream website. Notice in the menu bar the link to technical documents. On clicking that link, you'll see the page reproduced here. This is a repository for the specification documents combined with various implementation notes that you may find useful. In delivering these latest IP packages, our aim was simply to help accelerate the adoption and integration of this open source serial interface protocol. To further help your own development projects, each package is supported with 2 fully synthesizable projects. Furthermore, we provide quick access to a simulation via multiple VHDL test branches. To close, I'd just like to run through a couple of the frequently asked questions that we get on the topic of ESIstream. As we saw earlier, when discussing beamforming, link latency is important, and as a result we often receive inquiries specifically on what we can do to reduce it. In the case of the existing IP packages, there are a number of steps you can take. Very simply, there are immediate benefits removing D-type flip-flops within the design. Users are completely free to modify and improve the designs we've supplied. Another option is to change the output buffer implementation. Stop using, for example, the flexible dual clock FIFO system and replace that with a single clock FIFO. Alternatively, an optimized shift register may suffice. Finally, another option is to change the transceiver configuration according to the FPGA manufacturer's datasheet and use an elastic buffer bypass instead. It's not unusual to need to adapt existing IP for a new FPGA platform. We provide documentation covering this topic on the ESIstream website. It's important to take care with timings, especially those associated with the new target FPGA. ESIstream uses two specific IP blocks within the FPGA. They are the high-speed transceiver and, in the case of the receive-decode circuit, the FIFO. In reality, adapting IP to your FPGA should not be too traumatic, especially when moving between FPGAs from the same vendor. Teledyne E2V eases migration with the release of our new packages, as we're supporting both Xilinx and Intel. And if you still feel you need some help, then contact our hotline. We have a dedicated contact point reachable at hotline-bdc@teledyne-e2v.com. I'd like to now highlight some useful link debug features embedded both in Teledyne E2V ESIstream enabled products, as well as the receive IP packages that we offer. What may not be immediately apparent is that the EV12 AQ600 data converter provides several useful features specifically to help diagnose link transmission problems. Two debug features are highlighted on the left of this slide. These are the test and data mode select options. The ADC provides an embedded pattern generator that will output either a linear ramp or a stream of null data on demand. The data mode select allows you to enable or disable the pseudo-random bit coding of the transmitted data. This considerably enhances debug, since you can now ensure that, even if you are uncertain the data converter is operating correctly, it can still be forced to output known bit streams. In this way, you can concentrate on validating the physical layer of the design. Link debug component features provide the following user controls. The ADC allows for the pseudo-random bit sequence lane encoding to be disabled, thus sending raw data over the link. For this reason, our receive IP includes the ability to configure itself to accept randomized coding or raw data. Without the PRBS coding, data words on the link are far easier to observe with conventional logic analyzers. The receive IP enables serial lane configuration, controlling which lane outputs which ADC cores data stream. And finally, the embedded pattern generator within the ADC either provides a linear ramp or null data on the serial digital outputs. This data can then be sent to one specific ADC output lane, irrespective of the status of the input sampled signals at any of the ADC cores. So each one of these features allows developers to set the link to known logical states, thus significantly aiding and accelerating the debug process. Thus far, we've only considered latency in the receive path, but what about the transmit latency? The figures shown here were simulated with the Vivado suite using a Xilinx KU040 with their GTH transceivers. In this case, we calculated a compound latency of 26.7 nanoseconds, typical for the transmit ESIstream IP path. Obviously, in budgeting for the full latency from data in to analog signal output, you'd need to factor in additional latency contributions from the physical interface, as well as that through the digital to analog converter itself. Well, we've reached the end now, and I'd like to quickly review today's discussion topics. I started by recapping the key features and benefits of ESIstream. We took some time to consider how to choose the correct IP package for your specific application, and learned that the selection was based on a trade-off between link latency and frame clock frequency. I then walked through starting a project before looking more carefully into detailed clocking schemes for the various supported data frame options. Finally, we considered some of the future developments ongoing, and in the last section I reviewed some of the many questions that our customers ask in respect to ESIstream. It now only remains for me to express my gratitude to you for sharing your time so generously with us today as we walk through this Get Going with ESIstream seminar. Many thanks for your attention. I encourage you to get familiar with this open source serial data link technology by exploring the resources on the ESIstream website. Also, if you're interested to more fully understand the unique sync chain feature of the EV12AQ600 discussed earlier, feel free to check out our short YouTube video linked here. This has been Mark Holdaway, and on behalf of the Teledyne E2V team, many thanks for being here, and goodbye until the next time.
Mark, thanks so much for that great presentation and for going over the most commonly asked questions. Now with that, we're going to wrap things up right there. So Mark Holdaway, thanks again for taking the time to be here with all of us today. Now we'd certainly like to say a special thank you to all of our audience members for being part of this webinar event. Take care and have yourselves a great rest of your day.